We start off with a clarification of some definitions. Dynamics is the study of bodies in motion. The two subfields that we can study would be kinematics and kinetics. Kinematics involves the study of bodies in motion, but without any regard to the forces that are involved. So these are just independent motion, whereas kinetics would involve including the effects of the forces. So dynamics is a general term. Kinematics is without forces involved. Kinetics is what's being involved. This is the body only. This is the body plus forces. Very often, a body that's being studied in a dynamic situation can be considered to be, if the body's not being deformed by the motion. And if it is a particle or made up of particles, then we often use a vector notation and say R, which is a vector, represents the position of that particle. If that's the case, then if R is the position, then the velocity of that particle is given by the derivative of R with respect to time. And this is simply written as a new vector v for velocity. If we're to take a derivative of the velocity with respect to time, this would give us an acceleration. It's written as a, an arrow over it. So this is the particle approach. These would be instantaneous velocities and accelerations, and this is one way of describing the kinematics of a particle. Now, if we were considering strictly linear motion, and in the case of linear motion, we're talking about the body moving in a straight line. And if we have linear motion, then we can write the following expressions. The position is normally indicated by S, and S may be a function of time. So the position along the straight line is changing as a function of time. The velocity is given by v of t, and v of t is equal to ds dt, and the acceleration is given by a of t. This is the rate of change of the velocity with respect to time. But now this in turn will be equal to the second derivative of s d2s dt squared. Now you can see some relationships here going back the other way. We can look at the velocity and say the velocity is given by the integral of the acceleration dt. And we can also say that the displacement, or the position, is given by the integral of v of t dt. But since v of t is the integral of a of t dt, we write as a double integral of a of t dt dt. So we can see how these three quantities are related to each other. It may be useful in some situations to work with the vector form. Let's go back to the vector form for just a minute. We're saying the position is given by a magnitude at some angle theta. So it's really a vector that we can show like this. And we can say this is the angle theta, this is length r. And we can describe this as the position of the particle within a coordinate system. Now if we're dealing with a rectangular coordinate system, we can write this as being equal to, let's say we have an I, j, and k components, where these are all unit vectors. So we would have something times I plus something times j plus something times k. So instead of using x, y, z. We want to say use an I, J, K coordinate system, where these are unit vectors. So this may be I, this may be J, and K is coming out of board. So if we did this, we can say that R in three-dimensional space has the vector description where this may be some length x, this may be some length y, this may be some length z, and these are just unit vectors to indicate the directions. Now if we were to differentiate this, v, which gives us a new vector, which is the velocity vector, we'd end up with basically x dot in the I direction plus y dot in the j direction plus z dot in the k direction, showing there are three components of the velocity corresponding to I, j, and k. And we can go one step further and say the acceleration would be given by x double dot in the I direction plus y double dot in the j direction plus z double dot in the k direction. So here we have again a system for describing these three components.